All right, here we go, my friends. I would love if you would be quieter. It's okay. Caitlin Bennett pointed out I had a mistake, which is extremely rare. Usually I am perfect. If you go to the chapter 1113 free response test help, I did this problem, and then at the end, like the last 2 or 3 minutes, I did the bonus question and I did it wrong even myself. I took the density times the volume and I said it was the mass of the solution, but it's the mass of the solvent. Oh man. Well, math wise, it is a huge mistake. How could I? I regret to inform you guys all that I've stopped being perfect as of that recording. It was a good run, let's be honest. That was a year ago. It was a 44-year run. Ask my mom. I'm pretty much perfect. Okay, so I wouldn't bother watching that last part. Now, I don't have a video of that except for yesterday we did those problems and I recorded yesterday. So they are on there. So anyway, just don't watch the last 3 minutes because that could get confusing. Fair enough. I don't actually have that bonus question on the test anymore because I have that type of question asked in a different section. Yeah. Oh yeah, who's that? Oh gosh. Oh, okay. Now I just think I'm going to hell. That's all. It's not Cooper's fault. It's my fault. All right, here we go. This is your test review. CH1113 AP test review. Whatever. I'm going to cover 2 chapters in the next 10 minutes. Sound bueno? All this is on the reader, so it's not like you've never seen this. Please remember your inter and intramolecular forces.
I need to understand what's going on. I don't know what it was. Last time I sat up here, I understood everything.
You weren't distracted by the awesome ladies in the back, probably.
That's probably what it was.
TA, I just have more of those to dry. Hold on. These still have bleach on them. I have a rinser over here. All right, so just dry those. You're the best. Okay. All right, make sure you remember intra, that's the top one, just had to read, are attractive forces within molecules. That's what we studied in chapter 11. These forces are generally referred to as covalent bonds. These forces give molecules their chemical properties. Next, inter are forces that exist between the molecules, like 2 water molecules to themselves. These forces determine the physical properties of liquids and solids, such as what type of properties we talked about a lot. Okay, that's a true word, but I'm looking for boiling point, freezing point, and one other thing, vapor pressure. Those are the 3 main things that we worried about with how these intermolecular forces interact. All right, the physical state of a substance depends on the balance of the kinetic energy or the temperature of the molecules and the attractive forces between them. All right, I don't understand, people. This is why the state of the substance can be determined by knowing its temperature. These forces determine the boiling point, melting point of the substance, and then later in the chapter we talked about vapor pressure. All right, in general, as the intermolecular forces increases, the melting and boiling point also increases. We have talked about that in lots of detail. All right, make sure you are familiar with these. Excuse me. an ion dipole force. That requires an ion and a dipole. So an ionic substance dissolved in a polar liquid would be what you're looking for to have ion dipole forces. Yes.
Are we gonna have any question where we have to have a flask? We like have to kind of say like a flask, and we have to say the different things.
Yeah, you will. All right, dipole, dipole. All right, that's polar to polar. So that'd be like two water molecules. All right. They can be the same. They cannot be the same as well, but they have to both be polar. So if I put water and methanol together, they would mix, but they would have dipole, dipole forces. If I put water and hexane together, they would not have forces between them, besides their London dispersion forces.
Don't they need to be similar, like polar-wise, like they would have similar polar charges, if they are to be dipole, dipole?
Yeah, like their dipoles have to be similar. It's like 1.5 to 2.1 or something like that. Or no, 0.5 to 2.1. You don't have to have that number. All right, London dispersion forces are forces created by induced dipoles. This is where you had something that had the nucleus. It has its electrons over here. And then another one, these electrons polarize the electrons of the other thing. All right, so you end up with a positive side and a negative side, just for a moment, because then the electrons could certainly go that way and the dipole could switch, but whatever. This results in a negative charge on one side and a positive charge on the other. These forces exist in all substances. So if Cooper, he's saying, if I have a flask, and I have to identify the forces in here, every single one of them, you better have LDF. All right, they all have that. Now, there might be others. So if it was salt water, we said that has all of them. Dipole, dipole between the water, ion dipole, dipole. Oh man, that was a massive itch I just got. I couldn't even focus.
That makes my dipole.
You're welcome.
Why would the dipole bipolar?
Because water has water molecules that are attracted to themselves.
Oh, yeah, right. So pretty much anything that's dissolved in water is going to be hydrogen.
Not necessarily,
Well, there will be.
because there's things that you can put in water that are not polar.
Yeah, my NaCl was polar, but the water still has dipole.
Okay, let me put it different. You can put non-polar things in water and they don't mix at all.
If they mix.
If they dissolve, I guess dissociate is the better word.
Na would be an ion.
Right?
And it would get dissolved, so that would be ion dipole.
Yes.
But then what would make, because I see what you're saying for water, but then how would anything that dissolves in water would be dipole?
There's always dipole between the water molecules still, but not water and hexane, because hexane doesn't have a dipole, so it'd be dipole and nothing. Go ahead. If it was, you guys are minutely analyzing this. If you had hexane in water, it would look like this. You would say, well, the hexane and water do not mix, but in hexane, there would be London dispersion forces, and that would be it, no more. In water, you would say there's London dispersion forces, hydrogen bonding, and dipole, dipole. If I poured salt in here, all right, here's my salt shaker, and it all goes through here. It goes straight through the hexane, and then it would dissolve in here. So then you'd have ion dipole. You would not have it here because salt doesn't do anything in hexane except for sink to the bottom. Speak, child.
Are we gonna have to do it in like the most important order?
No,
So we're going to be overthinking the heck out of it right now.
it's fine. There are questions like this, so
But NaCl, you would still say, yeah, dipole, dipole is the water.
right.
Say hydrogen is the water.
Okay. Okay.
Yeah.
Forgot about what? Pizza. Oh yeah, right. No, because I'm a scientist. I have the data to support my hypothesis. There's no chance in hell of it actually happening. I know.
I've never been doing this smart. I love it.
I didn't. That's a location.
Yeah.
You said the H word twice now.
It's a location.
One time you said I'm going to H.
Both of those, I'm trying to give you a rough,
Cooper, don't say that word.
anyway, here we go.
Cooper, can you please?
It makes me laugh.
Okay, here we go. Shh, we're wasting your own time. Hydrogen bonding is a very strong form of dipole-dipole bonding. Hydrogen bonding exists only between hydrogen and atoms bonded to F, O, and N.
Why is it stronger? Is it just because there's such?
It's a greater dipole difference,
Okay.
so that makes it
It'd
stronger.
be like a 0.5 to a 2.1.
This is a 1.5. The difference between that, this is, what is it? It's a 2.6 between F and H. You don't have to know those numbers, by the way. I'm just trying to remember them.
Yeah, but it's
Okay.
so strong that it's like almost, because that's why it's bonding rather than.
Then
Hold
it's,
on, ignore me. I'm thinking. but
Okay.
Yeah, I agree.
to determine what type of IMF is dominant, check the type of bonds involved. If there's an ionic and a polar substance, the IMF will be ion dipole. If they're both polar, it'll be dipole dipole. If there are only non-polar, it's London dispersion forces, LDS. On the test, especially the AP test, put LDF. Don't waste your time writing out London dispersion forces. Oh, for sure. They don't even want to read London dispersion forces. All right. Now, we're from Utah. Don't accidentally put an S.
Oh, yeah.
They
All right.
probably laugh.
And then don't switch the D and the S to the LS.
London.
That would be if you're in Oregon.
Okay, here we go. We already did this, so I'm not going to do it. You can go back and watch the first day of chapter 11 class videos. We already did this, but yes, there will be problems like this where I give you something and you have to describe the IMF for each one of them. It's not. I mean, there's a chance, but I will tell you the chance is 0. Okay, here we go. Vapor pressure. As discussed last chapter, vapor pressure is the pressure of a gas above a liquid. Liquid substances of low molar mass and weak IMF tend to have high vapor pressures. Remember, high vapor pressures, it might seem weird, but it means there's a ton of stuff above it. A high vapor pressure means that it evaporates easily. Okay, because the vapor pressure, we're talking about the stuff above, nothing really in the liquid, the stuff above it. Okay, so things that have weak IMFs means they don't hold on to each other very tight. So they evaporate easily, which means they have high vapor pressures.
That would be
You
the
okay with that?
line.
Yep. Yep. I would put it the other way around because the causality is the reverse, but the relationship is the same. Okay, then a high or a low vapor pressure would mean not as much. And that means it evaporates slowly or it requires more heat to evaporate. So this would have a higher boiling point. This would have a low boiling point.
Because it's easier for it to.
Right.
As a force, I mean,
Yep. Correct. So boiling point is when the vapor pressure of the liquid matches the atmospheric pressure. So essentially it's saying the ability of it to leave equals the ability of it to stay. So it just starts to leave, like it evaporates very quickly. We put energy in, now they can all start to leave. They don't all leave immediately. That'd be crazy. Hits the boiling point and boom. Your mac and cheese is just whatever. Like, no, that'd be like ice turned into steam directly.
Yeah, dry.
Your mac and cheese, if you went to boil the water, but the water, once it reached the boiling point, every part of it turned to gas, you would never be able to cook your food. You could. Okay, make sure you can explain stuff like this. I read over them last night or yesterday in the class. I didn't show them, but I read over every single question you'd have to be able to explain. Remember that part?
So that would be a crucial video to probably watch.
You would be dumb to not watch it, pause it, and make sure you can answer every single thing I just said. Okay, so we know that boiling point is affected by IMFs, right? So what affects IMFs?
the-
All right,
How large.
their
they are,
size.
if it has high bonds,
All right,
how
pi,
separated
versus sigma. That's not on the test, by the way, but awesome job, Reese.
Oh, thank you. I was
All right.
all the-
I'm going to say polarity.
Can you say temperature for sure?
No.
You can't say temperature?
Temperature doesn't have it. The
IMF effect.
like we're talking about how temperature is affecting it. So I wouldn't say temperature affects the temperature because that would be dumb. In order to get something to boil, I put the heat in.
Not like the outside, like.
Right.
temperature. Okay.
Okay. Now the polarity, and then make sure you understand that, you know, if it's a large molecule, it has a greater ability to be polarized. That's the polarizability or the squashiness that guy loves to use in that one video. All right, know that things that have hydrogen bonding will have higher melting and boiling points than things that don't. So the more polar and hydrogen bonding and the larger, those are the things that will have the high, and then things that don't have the low. So like gasoline is C8H18, and it is a gas, or sorry, it's a liquid at room temperature. Okay, propane that you burn when you cook your food on your barbecue is C3H8, and it's a gas at room temperature.
Oh,
So
we
it'd
did
it'd be
that.
because of size.
So it has to do with size. Okay, easy enough. Okay, propane is C3H8. Propanol is isopropyl alcohol, essentially. It's C3H7OH. Gas at room temperature, liquid. Why?
Because of hydrogen bonding.
All right. So your answer should say because propanol has hydrogen bonding, which increases the intermolecular forces or something. So don't just say because of hydrogen bonding, which I know that's the right answer, but be just a tiny bit more specific.
Because hydrogen bonding increases IMF.
Okay, there you go.
What that word?
Oh, because it has to.
How is it now?
Or an N, or an N.
Or an F.
That is because the city guide is not fitted.
So what would we,
So I got another day to do.
What?
give us an example of how we would answer that? Because hydrogen bonding affects the IMF and it's.
I would say because propanol has hydrogen bonding, which gives it greater intermolecular forces
Okay.
and raises the boiling or melting point. This one would be boiling, but either way. Okay. Yeah. There's a thing out there called naphthalene. It's the main component of mothballs. So the main component of your grandparents smelling weird.
I actually love old
Oh, yeah, Cooper. Cooper, didn't you also hit on Bert's wife?
I hope that
Yes.
comes. I hope that comes across on the video.
All right. This is not drawn perfect, but it's something like that. It's two hexagons, 1, 2, 3, 4, 5, 6. Yeah, tied together. This is nothing but C's and H's. And I don't remember, I don't have it drawn right, so I don't remember. But this is a solid at room temperature. There's pi bonds. It's a large molecule. It's a complex shape. So all sorts of reasons, this is a solid. Now, if you get it very warm at all, it pretty much, it sublimates.
So it turns straight to gas.
Yeah, and that gas smells bad unless you're Cooper, right? And so older people own clothes that are made out of real stuff. Because like most of what I'm wearing right now is made out of gas, like oil. It's fake. Old people own wool and real cotton clothes, and moths love wool. So what a older person will do is they store their real wool coat that they wear like once every 4 years when they go play pinochle with Betty. All right. They don't want the moth to eat the wool because they do eat wool. So they put mothballs in there. The moth smells that and stays the heck away.
But Cooper is
Yeah,
drawn
and
right
Cooper
for
was
you.
not.
Well, it's fine.
The Cooper moth just goes right in. He's like,
Cooper probably has a really nice grandma and it reminds him of her. So it doesn't mean he's a cougar. Okay, here we go. Next. Phase diagrams show the relationship between temperature, pressure, and the state of matter the substance is in. The line represents the boiling and melting point under, or the lines. All right, so which one, tell your partner, is representing the boiling point? All right, so hopefully you said this line right here, right? Because when a liquid goes to a gas, it boils, which would mean that this is the
If you had to
freezing
choose
point.
one point in particular, though,
Shh, what?
if you had to choose one point in particular, though, which one would you choose?
I wouldn't choose a point. I would choose a segment and say A to D.
The point is normal point. So isn't point D, I tried to vocab, isn't that critical point? Because that's where they all.
Yeah, beyond this, it's indistinguishable. Yeah. Okay, so I think it was Judah just said this. This is the normal freezing point, normal boiling point. And then this is the triple point. This is where all three can exist at the same time.
What's the difference between critical point, critical pressure, and critical whatever?
I don't remember. To be
Those are the hardest ones.
I know, to be completely honest, I don't remember either. So
They're so hard.
Merry Christmas. No, that doesn't mean don't worry about it.
Wait, and so you worry about it?
I can hold you responsible for something I don't remember. I'm not taking the AP test.
Sure, actually, I forgot, like, we have to prepare for the AP.
Weird. I don't. I get paid either way.
I'm taking three tests.
The
oh wait, yeah.
critical pressure and critical temperature are the same idea. They're indistinguishable beyond that point, but one's based on the pressure, one's based on the temperature.
Yeah.
So they're really similar. They just are based on the different unit.
Doesn't critical pressure need to have to be at a critical temperature?
Yes. I know that much.
So to get critical pressure, you need critical temperature.
And it's for a gas to turn to, or be indistinguishable.
From a liquid, which is unimaginable. So that's like, what? I don't know.
Why do we need to know that? I looked it up, it's really cool.
Like,
Okay.
I wanna, like, eat triple point, like, oxygen.
Triple point oxygen.
Molly smells old people.
I'm like,
He smells triple point oxygen.
Okay, what's the difference between these lines?
What's the difference between the graph?
What?
Negative slope and positive slope.
All right, negative slope here, positive slope here. Water is weird. All right, it's one of the only ones with a negative slope between for the freezing point, essentially. That has to do with its hydrogen bonding and the space provided so that we can increase pressure and we melt. That is not always how things work. Usually we increase pressure and we make the solid more dense. All right, that's that. Make sure you're familiar with these.
But it gets less dense with more pressure. Well,
For water, it's
For
the
water.
only one, and only for a little part of that curve. Now, I know it looks long, but under normal pressure, it's just for a very small moment in time. All right, triple point, we already said that. So why do we never find carbon dioxide in nature? Because the pressure is too high to have that.
but if you had it in a controlled environment, when you could figure out, like, how
Yeah.
to maintain.
Yeah, if you had a piston and you could compress it and the walls were clear, you could certainly look in there and see liquid carbon dioxide. And honestly, trucks all day, every day drive down the road with liquid carbon dioxide. You'll see them. They're the trucks that have tons of metal tubes on their trailers.
That old apartment complex, this is the gastronomy center, and they have liquid oxygen, like a big tank of.
Interesting. All right.
You should have drank. I think as soon as you
Oh.
opened it, it would turn straight to.
Listen, this is crazy. I don't remember where it was. It was somewhere in the south, but just like within the last 2 weeks, I think it was 6 people died in a nitrogen leak. And you're like, well, what? And then I read it, and it was a liquid nitrogen leak because nitrogen is not going to kill you. We are breathing it more right now than we are. I'm like, how did they die? Well, they froze. It killed them like that. It's not. It's hold on. It's pressurized, and then the tank. There was some sort of massive leak, maybe a breach in the tank, and so the liquid rolls out, and then it does evaporate quick, but not before it froze them, and killed them. Yeah, it was like a meat processing plant or something like that. Okay, draw this and draw this. Ready, go. Okay, sorry, I did forget.
My old elementary school had in the same year, had mold and the monoxide.
Oh, carbon monoxide leaks are nasty.
What does it do to your body?
It poisons it, and it can change the chemistry of your blood for months, which affects your whole body forever. Okay, here,
Different blood.
do it.
Silver is
AgNO3, yes. I don't know about that last line. No. Nope. Oh my. But yeah, but then it looks like I used a line tool. I'll take it. It's for you to draw.
So do we need to draw the charges on the water molecule, or do you think they won't care?
You don't have to draw the charges as long as the circles are oriented the right way.
Okay, so like the 2 small circles.
Mhm.
That's a very good circle. I think I did this.
Now, the AP test could use the word solvates or solvated. That means the same as dissolves in or dissociates. Lots of words here.
Wow.
He's really good at it.
That's my man, Bert.
It's just how Bert is.
It's small because it's positive.
Yes, it's small because it has less electron to electron. Yes, Cooper.
Cooper, you supposed to know old people.
What?
Do you want to label the plus?
I would for sure. If you put CA in there, then it's just wrong. CA, what? Put +2 because it is a +2. They're picky. They're super picky. Yeah, if you put a Ca, that's solid calcium. If you put Ca +1, that's calcium with a +1, which would be extremely reactive. What? Yeah, that's because that's what it is.
So you have to do a +2.
Yep. Now, my drawing, I don't have a ton of space, so you'd have Cl minus, and you'd have two of them, right?
We have to draw two of them.
Yeah, for sure. Why do you have to draw two of them?
Because there's two reacted with the one CA.
Yeah, if you don't write the right ratio, they'll mark it wrong. You don't put the right charges, they'll mark it wrong. You don't put the right orientation, they'll mark it wrong.
Would that be right? So it's H2O to connect to this plus.
Yeah, I'm all right with that.
Wait, no, AC and then top two.
Down here? No, there's not two CLs here. Okay, I'll draw my beaker bigger, my cup.
Oh, I should do the next one. Hold on, don't start the next one.
Okay. Are we out of here in 4 minutes or 14?
14.
Okay. We're not going to get much review on the math, but we had that yesterday. We have it online.
That's a good point. AG, NO3, NO3 just -1.
Mega what?
NO3 just -1.
Yep.
So how would AG and NO3 go together as well?
This is over as a plus one. They're a perfect union.
Wait, AG is a +1 and it be a +2?
No, it's okay.
You can't make up your own chemistry.
You can, but I will grade it based on reality.
That's what I thought. I was like, is it AG or AU? I was like, silver and gold are real confusing right now. I swear, I know this.
Okay, in this drawing, which ion will I not draw?
Won't draw AC
I will not draw Ag.
because it's part
So
of the limiting reaction.
I'm going to put AgCl right here. Yep, well, why'd I do that? That was stupid. I did not mean to put a minus. That was just bad. I hate myself too. All right, that is solid. Okay, now that means I have everything else in here, correct? So I'm going to have some Na plus, and have some Cl minus, some NO3 minus. All right, we okay with that? Now, the positive was the smaller of the two. They will never nitpick on whether Cl minus or NO3 minus. That, I mean, this one's bigger because it consists of four things, but they're not going to care about that. And then, you know, honestly, this would be good enough most likely for this one. But if they said like also how it dissolves, then yeah, then you would have the O and the O.
Would they talk about the points if we put the water molecule?
Nope.
Because it is true.
Right. All this problem is really trying to get at is without doing math, it's trying to get you to illustrate, you know, that something that is limiting and the precipitate is not in solution.
Oh, okay.
That's really all they're looking for. All right. Sometimes, one second, just 1 second. Sometimes it will say, illustrate their, how do they put it? They basically tell you to illustrate the concentration of the ion by size. So what they mean by that is you would have, if you have a higher concentration, and then it would give you numbers. And so you're like, oh, it has a lot of Cl or a lot of NO3. So it was asking you to write a big NO3 minus, and then like you would, you put like a little Na plus, but that's pretty rare, but they could do that. All right. Oh, is that where you were going? By ion size. That's a great idea. What would you like?
Yeah, so what's the something with mass that looks like the reason behind why one?
Well, let's see. Would answer me this. Will this solution conduct electricity? Yes. Why? All right, it has electrolytes. That means charges. It has to have at least plus and minus charges to conduct.
I just remember
What?
Or like-
No,
It has to have both.
it has to have both.
So it's about kind of mixes with
Where's
each other.
that
If
one?
the substance is all like you're probably gonna give us some text or something, then all we have to say is does it have ions?
You would check to see if it can form ions. That's all you need to know.
But any sample type of
What's something that wouldn't form
Right.
in order to conduct electricity.
Yep. If I said you had water, if I asked, does water conduct? You would say, no.
No, no.
Pure water does not conduct.
Oh, but I was thinking about like lakes, how they have.
Right.
salt.
If I asked you, I don't know why I wrote that up there, would hexane conduct? And hexane would give you the formula, it'd be C6H14. And you'd say, no, I don't know why I did what I did right there. It bugs me too, by the way. Right. It has to be a solution of an ionic compound and
It can't be
polar.
a pure substance.
Because if I said this was hexane and salt, would it conduct? No.
Because it doesn't dissolve.
The salt goes straight to the bottom in
It
hexane.
has to dissolve and it can't be a pure substance.
Hexane is a, well, hexane's a polar and it's a non.
No, it's a nonpolar.
What is that?
That says a dissolved ionic substance.
Yeah.
Shh. It has to be an ionic solution to conduct electricity, or it has to be a piece of metal. That works too,
So the only pure substance that will ever conduct electricity is what?
or metals.
So with H2O and hexane, do we just have to like know that? Or like how come it wouldn't?
You should know that
Because it's
How come
just
it
a
doesn't
low.
dissociate?
because there's no, oh, here?
Yeah.
Because this is a non-polar substance. The reason you would know that is it just has C's and H's. It really needs to have, it needs to have an oxygen, fluorine, or nitrogen in it pretty much to be that way. Go ahead.
So if it's like, can it still get like energy from electricity though? Cause like, the milk gases, they like.
Okay, so that's a whole different type of science. And we would not do that. I guess you could if you could make sure there was no oxygen present at all, because those would explode beyond belief if we did what we did. So what we have the gas and not gasoline. We need to have a gas. We need to have its protons and neutrons here in the nucleus, and then its outermost electrons. All we're doing with this in a neon light or something is we are electrifying that to get it to jump up, and then it falls down. And our,
Because the falling down creates light.
yeah, then it gives off certain colors. So technically, I guess you could do this, but really probably it'd be hard. Yes,
Hexane and propane, they're both non-polar. Wouldn't they dissolve together?
they could
But it
technically.
wouldn't create electrolytes.
No, because they don't dissociate like ionic things do.
So
And
if you have an acid.
acids, a strong acid conducts electricity. We showed that in chapter 4. Weak acids sort of do. If you remember, vinegar lit my light bulb up a tiny bit, but HCl made it hurt your eyes.
Is there an answer key for the math on the back?
Usually I do it in class. I guarantee if you go onto my YouTube and you look at 2019 videos, you could probably find them all. But we're gonna run out of time, but that's where we're headed. This one you don't need to do.
Will we have these formulas to parts and reflection and stuff?
Yeah, no, they're given to you.
Even though,
Uh-huh. Okay, colligative properties, they are vapor pressure lowering, boiling point elevation, freezing point depression. All right, this is on the reader, and then we were supposed to do the math today. So, Raoult's law. And yes, all the equations will be given to you today. So I need PA, that's what I'm solving for. This gives it to me different than the ones we did in class. Oh man, I bet that was way quiet. If you watch the video, it might be pretty quiet. I apologize. I didn't realize that was so low. All right, so I got to calculate the vapor pressure of water above a solution prepared by adding 22.5 grams of lactose. Usually, not usually, last time I gave you the molality or the moles right off the bat. So this one, it gives you the grams of the solute, the grams of the solvent. You need to find the mole ratio. So you would take 22.5 and divide it by the molar mass of this. I think it's 354. It's been a while. Did you do it, Nisha?
I can.
144.
All right. So that would give you the moles of lactose. All right. It is 354? 342. Oh. It had been a year. That gives you the moles of lactose. Then you take 200 and do what? Divide by 18. Tell me that number, somebody. All right, 11.11. All right, now, which one of these numbers, what's this answer, by the way?
That is 0.06. No.
Okay, either way. Which one of these will be in the numerator? Moles of water. Moles of water. We want the solvent. So we got 11.11 over 11.11 plus 0.066. And this is going to be close to 1. It's not going to be very different. Probably 0.99 something. Well, maybe like 0.994. What is this? That's the mole ratio, right? So we take this 0.994, multiply by the given pressure, and that gives me my new vapor pressure.
So pretty much whenever you know that it's going to be a vapor pressure problem, without flaws, vapor pressure.
Yeah, of a solution.
On the test, we get how much you get the more mass of a molecule that is.
Well, it's not that big, but yeah, you'll have to find a molar mass of something. I don't know, this problem makes me feel kind of intolerant. Oh, okay. What was the answer? Anybody? 180 something. Okay, not too hard, right? There's a problem just like this, just like it. Okay, boiling point elevation. All right, this one's easy because it gives you the molality of this one. Using data from 13.4. Oh, yeah, right. Let me. I need a chair. Is that on your sheet?
Yeah, that's how small it is.
Okay, well, 13.4, that table can be found in your book in chapter 13. It's the fourth table. You're all welcome. All right. So this is, we want the freezing and boiling point of this. So what it would tell me the normal boiling point right here. That says normal boiling point in Celsius. It would give me KB. It would give me the normal freezing point, and it'd give me KF. And I would just plug it in. It gives me, okay, toe. Oh. It gives me my toes just cramped. It happens all the time. I'm old.
It's just like curls up.
Yeah, it just goes like that. Yes. If your toes haven't cramped, have you even lived?